Hello everyone, this is Adhish. I'm a grade 10 student from Mumbai. So today's problem is visiting friends. The difficulty level of this problem is easy medium because you only need to know what the condensation graph is. And the condensation graph is basically the graph formed by compressing all strongly connected components in the given directed graph by using either Taugen's or Kusaraju's algorithm for finding strongly connected components. So a condensation graph is basically a directed acyclic graph in which we compress all the SCCs and we can find the SCCs and compress them by using either Taugen's or Kusaraji's algorithm. So basically in this problem we are basically given a directed graph with n nodes and m edges, and we need to find out, so each node has some number of people living in that node, and we need to find the maximum number of people you can visit by starting at a particular node. So for every node, we need to find out what is the maximum number of people which we can visit if we start at that node. So for example, let's say that we have 7 nodes and 8 edges. So the first thing which we can do is we can consider all the cycles which are there in the graph and we can compress them, because if we compress a cycle, then we know that for every node in that cycle we can visit every other node. That's why we can essentially visit all nodes in that cycle and end up in anywhere in that cycle. That's why I formed a new graph which compresses all the cycles, and in the algorithm it will basically use Kosaraju's algorithm to compress all these strongly connected components. So in this case there's only one strongly connected component and we compress them to form this single node. And now we can label that the number of people in each node is 1, 6, 7, and for this compressed node it will be 2 plus 3 plus 4 plus 5, which is 14, because in the example they gave 1, 2, 3, 4, 5, 6, 7 as the number of people living in each node. That's why 1, 6, 7 and 14 will be the number of people in each connected component. And now this is basically the condensation graph which we have formed. And the reason why we formed this graph is because of what I just said. Every cycle or every strongly connected component can visit each other. That's why we can form this kind of graph. And this is a directed acyclic graph. So now for this directed acyclic graph, we can use dynamic programming to compute what is the number of nodes which you can visit. So for example, let's say that initially we know for each of the nodes which don't have any neighbors, we know that dp of 6 is 6 and dp of 7 is 7. Then dp for each of these nodes 2, 3, 4, 5 is equal to 14 plus the maximum of these two. So the optimal value out of these two will be 21, and dp of 1 will just be 1 plus 21, which is 22. And that's basically why the answer would be 22, 21 for 2, 3, 4, 5, and then 6 and then 7 for nodes 6 and 7. Now before I explain the final algorithm which we'll use for the last subtask, I'll be briefly going over the first two subtasks. So in the first subtask we are basically given an undirected graph, because we know that if there's an edge from u to v, there's also an edge from v to u. That's why in the undirected graph we can just find out using a depth first search or breadth first search what is the total number of people for each connected component, and then we can basically for each connected component print the total number of people in that connected component. So for each node going from 1 to n, we'll just print what is the number of people, total number of people, the total population for all nodes in that connected component, and that can be done easily using breadth first search or depth first search in O of n plus m. For the second subtask, we are given a directed acyclic graph. That's why we can directly use the dynamic programming on this directed acyclic graph without forming the condensation graph. And for the last subtask, we need to form the condensation graph and then use dp on the DAG. So now I'll be explaining the final steps. So the first step is to form the condensation graph by using either Kosaraju's or Tarjan's algorithm. And basically this ensures that all the cycles are removed, and this basically ensures that we get a directed acyclic graph. So it brings us basically to subtask 2. Now I'll be describing the solution for subtask 2. So the answer for the DAG will basically be, we'll use dp of u to represent. dp of u is max number of people we can visit if we start at node u. And in order to compute dp of u, we'll need to go through. So for example, let's say we were computing dp of node 1, and let's say that these were the edges. Let's say that we had let's say we had k number of children. So let's say that these were the edges. Then in this case, let's say that there were k children. Then in this case, dp of 1 will just be the number of children in the node 1, or like, since we are so c of 1 represents the number of children in node 1, but since we may get multiple nodes in that connected component, in that strongly connected component, that's why we can represent. So let's say tot of I represents the sum of all cu, u belonging to a strongly connected component of node I. So basically all those nodes which have the strongly connected component number I, we'll add up the cu values for all such nodes u and get tot of I. That's why initially dp of 1 will be tot of 1, and it will basically be it will be tot of 1 plus the max of dp vi for I going from 1 to k, and this is basically going to be dp1. And in general, we can compute that dp of u will be tot of u, which represents the total population for the strongly connected component u, plus the max for all opposite edges. So basically, to get the children vi, we need to so we can store the edges in the normal way. So after when we are forming the condensation graph, we'll need to add these edges. So I'll show you in the code how we do that, but this is going to be the general idea, that we go and compute dp of u is max dp vi plus the tot of u, and that's basically the idea which I showed you worked for the example. And in general, this will easily work because we need to find the maximum number of people which we can visit, and since the condensation graph is a directed acyclic graph, we can just use dynamic programming in this manner to find the maximum number of people you can visit if you start at node u. So now I'll just show you the code implementing the same idea. So in the code, I use some pre-written code to facilitate the use of vectors, so you can just pause the video and see that if you want. Then I store global variables n and m. I have two adjacency lists. The first adjacency list will give us the actual graph, and the second adjacency list will give us the condensation graph. So we use those two adjacency lists to represent those two graphs. Then I store some methods. I'm basically using Kosaraju's algorithm. That's why I store SCCs, the discovery value, the low value. Ci represents the initial population for each node I. Tot I represents the population in the condensation graph. dpi represents the final value for the node I, or basically for the node in the condensation graph. And I have is on stack and visited. So initially I run Kosaraju's algorithm, and in Kosaraju's algorithm I do the exact normal thing, except I add to the current. So whenever I extract the node from the stack, and whenever this node is going to be part of the uh, SCC numbereth strongly connected component, in that case I'll mark SCC of that node to be this number, and I'll increase the dp value by c of v, or basically I can just increase the tot of SCC number by c of v, because tot represents the total number of total population for SCC number. And then I basically increase tot of SCC number by c of u, because u is also added, and I assign dp of SCC number to be tot of SCC number initially, because that's the base case for the dp, and the recurrence is what I showed you. So that's what I do in the first DFS. In the main method, I initially use fast IO, and for I take in the NM and the CI values. Then I store the edges using this is basically the first graph, and then after I run Kushraju's algorithm, I form the condensation graph by adding the two connected components together. So for all edges in the initial list, so if we represent U to be edges of I of 0 and V to be edges of I of 1, then in this case, if the two nodes are not in the same strongly connected component, so if SCC of U is not equal to SCC of V, then we add an edge between these two nodes in the condensation graph. Otherwise, we know that these two nodes are the same node in the condensation graph. That's why we don't add an edge between them. And then I basically do the DP. So for the dynamic programming, for all I going from 1 less than or equal to SCC number minus 1, because SCC number will be increased by 1 after we find the SCC. That's why we don't want to. So SCC number increases by 1 over here. So the last SCC number won't actually exist. That's why we go till SCC number minus 1. Then we compute dp of I to be max dp of I, comma dp of u plus tot I, as I just mentioned in the recurrence. Or we could just represent LL to be initially 0, and we could take mx is maximum of mx comma dp of u, and dp of I is equal to mx plus tot of I. That way is also fine. Both ways work, and in the end, for each I going from 1 to n, we find the SCC number and print dp value for the SCC, because we are doing dynamic programming on the condensation graph. That's why we need to find the node in the condensation graph, which is given by the strongly connected component of I, and we print that dp value. And now I'll just submit this code to see that it gets accepted. So as you could see, my code got accepted. I hope you liked this problem and my solution. If you had any doubts, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up.